Welcome to the first of 3 videos on dimensionless numbers in the brewery. This video will be online for free for probably about a month, and then I'll throw it behind a paywall. The first part introduces dimensionless numbers through 2 practical examples from my time at Clear Lake Brewing Company. The second part tries to refine those 2 examples using our understanding of beer knowledge. The third part looks at some other examples that we could apply in the brewery to try to show how the concept can be applied more broadly. So the first question you might ask is, why develop an age score at all? Why are we bothering with this? And the reason we're bothering is because, when you're out in the field, when you're working with breweries that are operational, that are making money, sometimes you have to work with what you're given. So basically there was a situation where the Radler we were canning at a craft brewery was exploding in the cans. Cans were going boom. Not a novel problem, not frankly a surprising problem given how we were handling the product, but still something we had to contend with. It was the most profitable item for the brewery to sell, so it was a big driving factor behind keeping it around. One of the things when you have a brewery that has a lawyer as one of its major operating officers is they'll insist on things like doing tests, and we found that when we kept the Radler in our cellar, that is at the brewery, that in fact the Radlers never exploded. The cans never popped, they didn't significantly re-ferment, the yeast was effectively stable below 8 Celsius. So the Radlers didn't explode at the brewery, it was when customers were taking them, putting them in the bottom of a boat, and going out fishing in a bright sun. The cans start to get warm, and kaboom. My initial recommendation of don't sell that was pretty much a non-starter. Because it was so profitable, because it was the second best-selling product, not selling it wasn't really an idea that they were going to be receptive to. So, the challenge for me was, do you stay or do you go? And given that I decided to stay, the question is, how do we deal with this issue? A big part of the challenge was communicating to the brewery staff as a whole that there was a big impact of storage temperature on product quality. Now, when we say that to brewers, it's an obvious point. Right? We know that storage temperature has a big impact on product quality, but not all the people that the brewery hires are going to be beer experts or even, beer enthusiasts. But we still need to communicate to them effectively the results of their choices. When you choose to go set up a special event rather than putting that pallet of cans directly into the cold room, when you choose to give it that extra few hours, there are impacts of that choice. And again, to brewers, this is obvious. To brewers who understand that, there's live yeast, it's an unfiltered beer with fresh sugar, the point is obvious. But to a lot of people who are more used to off-the-shelf beers, it's a more academic point. So, what to do? Given that the Radler was integral to the fiscal security of the brewery, there's 3 kind of big questions that come up. And these are truly kind of actually engineering questions more than they are brewing questions. But really anything that touches sort of food safety or beer safety, these are really good questions to ask. How do we manage the risk? How do we minimize the risk? And how do we even measure the risk or estimate it? Now, of course, that's assuming that we can't eliminate the risk. And we decided that between the financial position of the brewery and the commitments that the brewery was making to its ingredients, that eliminating the risk wasn't a possibility. So manage, minimize, and measure. As experienced professional brewers, we'll often have pretty good feel overall for the products that we have in our brewery and how they actually behave. If you go to a seasoned craft brewer who is, on top of their game at a small brewery, and you say, hey, I had this can of your extra special IPA, and it was kind of sitting in my cold cellar for 2 months, and then it was in the back of my pickup truck for a day, and then I put it in the fridge for a week. Is it going to be fine? Usually, they'll have a pretty good idea whether the answer to that question is probably yes or probably no. No, either because they have a good understanding of their product from a theoretical perspective, or because they've just tried that. But not everyone in the brewery is a professional brewer. The team needed something that any person at the brewery could look up and start to see the direct results of their choices in action. The choices that they made with respect to beer quality would directly impact things like their tips and the brewery's overall stability in sales. So there was interest too from the staff in understanding what exactly was going on. Why was it okay to maybe leave the IPA out for a little bit, but definitely not okay to leave the Radler out? So very much the question we wanted to answer then is, how warm is too warm? How bad will it be if I just leave the beer here? And how do we manage stock on the fly? I was literally getting calls and texts in the middle of the night saying, look, so-and-so just came back from this special event. They've got 5 untapped kegs of beer. It's been kept on ice all day. Do I have to unload the cold room by myself so that I can restock it to actually fit everything inside? Or can this wait until morning? And it's a very good question that somebody asked. Thank goodness they asked. But, in terms of replying to it, obviously texting me in the middle of the night wasn't the best solution. And, my initial instructions of always keep the beer cold was perfectly sound, and yet we see in the end that they really needed a little bit more than that. So this is really what drove the development of the age score and the must-sell score. A way to keep track of how relatively mature the beer was getting in a given set of circumstances for a given beer, and how fast you should try to sell each product. How much should I put this on sale to try to get this sold this weekend, as opposed to another beer that I've got in the fridge? So this desire to compare a similar product in dissimilar situations based on a few given criteria is very much what dimensionless numbers were made for. Enough of the why for what I did, down to the what of what I did. Now, the name Dimensionless Numbers can be a little bit intimidating. Try not to get off track. It's not that scary. The math in here is not that bad. Just try to keep track of the units you use. So, in order to understand what a dimensionless number is, we have to remember what a dimension is. Sometimes a dimension refers to sort of a measurement like 62 inches by, 92 millimeters. In this case, dimension just means units. When we're measuring something, it might be inches, it might be millimeters, it might be degrees Kelvin, it might be kilograms, literally anything that specifies a unit or what exactly we're talking about is going to be a dimension. And what's more, most of the numbers we use have dimension to them. It's relatively rare that we actually deal with pure math numbers that do not have any dimension. Put most simply, a dimensionless number is a number without dimension. And that's a bit of an irritating definition. More practically, it's a number we've made where we've ensured that all of the units cancel out in the end. Canceling out the units means that either through multiplication or division, the units all cancel each other out on the top and bottom of our fractions. Meters cancels out meters, seconds cancels out seconds. It's very much a case of turtles all the way down with this one. The same principle of all the units canceling out keeps applying, over and over again. So it's good news. You've used them before. We've all used them before. In fact, you just didn't know you were using them. Most percentages you work with are actually dimensionless numbers. Okay? When you have a sensory test and you have a number of samples that pass and a number of samples that fail and a total number of samples, well, you get a pass-fail rate. Those are both percentages, those are both dimensionless numbers. When we're in the brewery and we have the liters of beer we lose to drain versus the liters of beer we actually sell, well, that's a loss percentage. Okay? But notice that in both those examples, you have number of failed samples per number of samples. Liters of beer per liters of beer. Okay? Alcohol percentage is not actually dimensionless. It's a rate. It's the liters of ethanol per liters of liquid. So be careful, things can get a little tricky. The following are other common examples that you might be familiar with, depending on your experience. Loss percentage, the Reynolds number, batting averages, the Rayleigh number, if you're into natural convection, income tax rate, and Mach number. All of these compare things relative to themselves and relative to some kind of normalized number. So the loss percentage, we're comparing how much beer we've made to how much we've lost. The Reynolds number combines a bunch of things to do with how a fluid behaves with how large an object is. Batting average allows you to compare different baseball players that may have competed in different years and even played different numbers of games. The Rayleigh number is really more of an extension of the Reynolds number, and it more looks at what happens when fluids are in free flow. Your income tax rate allows you to compare taxes between tax brackets, but with various incomes within those brackets. Right? It's a way to try to make things fair. The Mach number compares the speed of an object relative to the sound across different fluids. So some of you may have seen this coming, but any dimensionless number combined with any other dimensionless number is still a dimensionless number. If it didn't have units before, it's not going to have units at the end. It's important you keep those separate because when we start mixing things, that's when we start to get actual results that we need to be cautious of. Okay, so this is probably the coolest part about dimensionless numbers, and it's the fact that you can just make them up. Always check for an existing dimensionless number first, but you can make them up to suit your own needs. You need to keep in mind what you're actually measuring though, and bad data leads to bad numbers. If you collect bad data, it doesn't matter what you do with your dimensionless number, it's going to give you junk. Most existing dimensionless numbers started off as pretty arbitrary in their formulation, and there's other ways you could write those same numbers and still use them. We don't because eventually one of them got popular, and people just like to keep things consistent. But that doesn't need to stop you from continuing to innovate and do new things. So comparing unlike things on an even keel is really the true gift of dimensionless numbers and the best thing that we use it for. You know, it's how you compare apples to oranges in terms of fruit. Okay? You can't compare apples and oranges because they are fundamentally different. But they're also fruit, they're also produce, and there's other ways in which we can call them similar or like. Once you have a dimensionless number, the very obvious question is, what on earth do you do with it? Mostly what you do with dimensionless numbers is you graph them. Sometimes you'll use them to rank or sort data as well. Right? You'll have a table of some group of things that you're studying and you want to find a way to bubble something up to the top. Useful dimensionless numbers will help show information and patterns in your datasets that were otherwise not obvious. Often the pattern that appears won't be exact. There's going to be a lot of noise in the data, but the more you graph and the more you sort of zoom out, the less noise you'll get, and you'll get less noise than if you were graphing the raw data separately. Once you've lumped it all together, it starts to iron out some of the little bits of variability. Looking back to the brewery and trying to answer some of our beer questions, there's a few aspects of dimensionless numbers that start to look really, really attractive, specifically the ability to compare similar but unlike items. Say beer and cider, for example. The usefulness of any dimensionless number that we make for the brewery would depend on three things: how we calculate the number, what we're going to use it for, and the quality of our incoming data. Recalling, of course, that crap in makes crap out. So some of the questions we might ask is, how much older should this given beer taste in a can that I've handled this way versus that same beer that's been in a growler that is fresher? Other questions might include, how well does this pilot batch sell for a pilot batch? Another question we could ask is, how well does this beer sell for its style? Perhaps we've made 3 or 4 lagers and they all sell well, but is that just because people like lagers at our brewery, or is it because one of them has been exceptional? There's really no limit to the questions we can start to ask. In our specific case, we wanted to establish a means to compare the relative staleness of several different types of beer that had been stored at different temperatures: cold cellar, a cold room, and out on the floor. The idea was to underline to the sales staff which beers should be sold the fastest for the best management of beer taste overall. Instead of managing beer sales just by production date, it was also managed by the age score. So the Radler that was a little bit younger was being pushed to be sold faster than the IPA that was a little bit older. We're going to begin with a simple formula for an age score that accounts for the biggest factors that affect staling that the brewery also had the means to measure and can control easily: the temperature of storage, the carbonation, the IBU, the alcohol percentage, the color, and by consequence the acidity, and the date of production. So I actually expect a lot of pushback from fellow brewers on excluding pH from this. And my justification is simple. The tools and time available at a very, very small craft brewery make measuring the pH by different staff members a variable process. And if you want to fight me on that, I say bring it. These are the components that we're going to use to develop our dimensionless numbers in the simple version. We have an age in days that we're going to establish very simply. We have a maximum beer age that has been arbitrarily assigned by me to be 1 year, measured in days. Later on, we'll use the starting packaged beer volume, that's how much we packaged on packaging day, and we'll also use the current packaged beer volume in inventory. we're going to develop a temperature scaling factor, and we're going to develop a beer style scaling factor. Now, the temperature scaling factor is a little bit more straightforward. It simply combines some of the known behaviors of beer scaling with respect to temperature of storage. The beer style scaling factor in this case will be developed a little bit more empirically. This is where our knowledge of brewing science and our products in particular really comes into play. You know, dimensionless numbers are only useful if we make them with intent, knowing what we're trying to get out of them and what the physical realities are in play. By bringing together a bunch of things that make beer go stale faster, by bringing together a bunch of things that keep beer fresher longer and pitting them against each other, we can push our number in the right direction, even if it's not 100% accurate. Okay? We can keep pushing things closer and closer to reality without having to worry about whether or not we're actually there yet. So now that we're talking about making this dimensionless number, and we've talked about what we're going to use, let's talk about the inherent limits. One of the big limits is going to be the things we've ignored, like the package O2 and the pH. The reason we've ignored those is mostly because of equipment and operator education restrictions. We've also ignored any impacts of infection. We haven't put any cell counts in here or any sort of infection metrics that we might use to control our level of infection, which will likewise worsen over time, much like any type of staling. Any of the limits we've already run into with any of the individual parts that are going to make up our final number will still bubble through to our final number. Errors get kind of inherited that way. Now, a very fair question would be, why on earth did we ignore the package type? And the only reason is that in this particular case, the beer game for this brewery at this point in time was so vastly different between cans and kegs, it didn't really matter to compare one to the other. The type of package that beer comes in and the way in which it is packaged will be a huge impact on how it maintains its quality over time and how it prevents infection or resists oxidation. In this case, the question was a bit academic because the length of time that a can would spend in this brewery would at most be about a month, depending on the style of beer, whereas the kegs could extend to well beyond that, again, depending on the style. So the beer style staling factor is relatively simple. The faster you think your beer is going to stale, the higher the beer style staling factor it gets. The better you think it keeps on the shelf, the lower the factor it gets. When I first did this, in a bit of a rush and using our best available tools, we did this with a dead reckoning method. What this means is that I took a series of samples from the cold room, lined them up, and did a great big sensory panel with me and the two other people that I thought had the best sensory palate in the brewery, and we assigned them a simple score for how stale they tasted on a scale of 1 to 5. I averaged and crunched those numbers to push them into the beer style staling factor. To make things easier, I identified the flagship brand of beer as having a staling factor of 1. This is establishing an arbitrary reference point, but it's one that's going to help us out, because if our flagship beer is kept at the best possible conditions, if that is our standard, then we're applying our best knowledge and care to the product that's going to make us the most money anyways. One of the other choices in here is identifying the flagship as having a value of 1. We could have also chosen 10, 100, 23.5, it doesn't really matter, but I wanted to make the math as simple as possible at the end of the day. We're going to spend the least amount of time on the temperature aging factor, in part because we go into it in more depth in the next presentation. Information gleaned from looking at the effects of pasteurization on beer and shelf life informs most of this section. The key takeaway here is that the impacts of temperature on the staling of beer are a logarithmic or exponential function. And so we have our first dimensionless number that we're actually going to use, our age score. It's got our current age in days divided by a baseline age of a year. I did that on the basis that after a year you should probably throw the beer out. We also have a temperature staling factor, which is going to influence how our beer matures versus how hot it gets. We also have a factor for what type of beer it is, and we also may have a factor for what type of package it's in, whether that's a keg, a can, or a growler, in the case of this brewery. Now that we have our formula, it's good to run through some examples to see how it actually gets applied. So let's look at the flagship beer of the brewery, that's been sitting around for about 30 days, a fairly typical scenario. A session ale packaged 30 days prior and stored at 4 degrees Celsius, fridge temperature, would have a staling factor as follows. A radler packaged 20 days prior, stored at 20 degrees Celsius, or say roughly room temperature, would have a staling factor that is much, much higher. This is good. These two examples show that the way we're calculating this number is giving us the results we want. We know that a radler that is stored in that fashion will be much more problematic than a session ale stored in the fashion that we've described here. This doesn't mean that we've rigorously tested it, but this is our good first waypoint to make sure we're pushing things in the right direction. So I've included some data here from our actual brewery production data at the time when I was applying this at Clear Lake. We're going to take that and we're going to apply our simple beer style staling factor and see what sort of results it produces. But let's start by doing a reality check. Firstly, we'll take a look at our reference beer that's been stored for 30 days, our typical case. We see that it has a relatively low score. This is good because this is our baseline flagship product and it's the one we're dealing with the most often. So if we've set our numbers up correctly, this should come in somewhere near the bottom. Secondly, we can see that the radler, when stored warm, has a very high score, as it should. We also see that the IPA has a more moderate staling, which is more consistent with that style and how the beer performed. Lastly, we see that the fresh amber ale that we just packaged, that we just put in this cool basement, has a score of 0. Because it was packaged today, and thus no matter what its temperature, based on our metric, it is absolutely fresh. Our metric does not break things down below the time unit of 1 day, but that's something that you could look at. When we graph this small subset of data, the large spike representing the radler that's been stored warm is very obvious to see. We also see the amber bottoming out at 0 in our range of we don't need to worry about it today. Also of note is that the IPA has started to creep up. Maybe it's time to put that on sale. So far, our age score has only looked at the beer we have and how we're storing it. It hasn't looked at how much of it we're storing. Some of those high-scoring items might be the last few bottles of an old batch. They might be squirreled away in the back of the cold room, mostly forgotten about. And this is where we start to transition from just managing beer quality to actually managing sales and warehouse. Because it's not just how stale the beer is, it's how much of it you have on site. 1 to 2 bottles of a stale beer is not really a problem. A pallet of beer that is going stale quickly is the problem you need to worry about. So now we're going to transition to the must-sell score. It's going to take the age score into account, and it's also going to look at our inventory stock we have on hand. So the way we're setting up our must-sell score, the less of something you have, the less pressure you will have to sell it. Now, if we don't apply this with any sense, without any consideration for actually managing a quality warehouse, we'll end up with a very large number of very small lots that will become increasingly old. This is potentially actually very useful for a brewery that's trying to cultivate a sort of vintage collection. We can also use some brute force logic in our spreadsheets to reject must-sell scores that are below a certain threshold if a beer is of a certain age. So let's go back to those earlier examples from Clear Lake and add in our inventory factors to generate our must-sell scores. Remember here that this is a sales-focused score, not an inventory management-focused score. So it's not necessarily going to prioritize the beer that is the most stale. Case in point, the radler being the most stale is not under as much sales pressure because there's not nearly as much of it. The amber that was absolutely fresh maintains a score of 0. Even though we have a high volume of it, it is very fresh. Because the beer is absolutely fresh, we're not really paying any penalty on having it in storage for at least today. Beers that are more stale and also high in inventory will build up to the top. In this case, the IPA shows this. Graphing that tabular data, it's a little bit easier to see the patterns jump out at us. The IPA that's older, that we have a lot of, is fairly high up there, but our radler that's also pretty stale is still on that chart as well. To better illustrate the difference between these two, I've graphed them together. The age score is using the left-hand axis. The must-sell score is using the right-hand axis. We see that when we graph these, there's a disparity between the age score and the must-sell score. And this is because they are prioritizing different items based on different factors. Now, there's probably quite a few of you that wonder a little bit as to why we've applied math to something as loosey-goosey as how stale we feel the beer is. Part of the reason why this isn't an inappropriate approach is because brewmasters and brewery professionals are trained tasters. We also have a clear idea of what the priority for our product is and what factors we wish to emphasize. Those are sometimes hard to put into data. Sometimes it's easier to achieve our best results by amplifying our best training. There are pros and cons to using this approach. It is simple, fast, and easy to do. We were able to develop these beer-style staling factors in an afternoon. A big con is that doing this was very, very empirical, very hands-on, and it was very, very easy for someone else to screw up, as happened about 8 months down the road. The next slide discusses a more analytical approach we could have used while still applying our same base principle of dimensionless numbers. So in the next presentation, I'll cover a more analytical and complicated method to look at the staling factors for a beer. While this is more scalable, it may not produce more useful results. If we do the job really, really well on our more analytical version, we'll be closer and closer to producing actually accurate results that will further normalize our data. I hope you found that video helpful. If you did, please like and leave me a comment below. If you didn't like it, I suppose you can leave me a comment anyways. If you'd like access to my slides, please message me directly. Otherwise, I'll see you in episode 2.